Okay, so the last bit of the haloalkanes topic, we need to talk about ozone depletion and how organic halogen compounds have caused this to happen. All right, let's think, what is ozone? All right, ozone is O3, and at ground level, ozone is a pollutant, causes breathing difficulties, but higher up in the atmosphere, there is quite a bit of O3 and it absorbs UV radiation, and that's very important because UV, of course, causes mutations and cause skin cancer in human beings, can cause mutations in plants and animals and so on. Let's just have a think about the bonding of O3. Well, what you have is you have O2, and then this one forms a dative bond to another oxygen. So if you drew a dot cross diagram of that, it would, so if I draw a double bond there, this oxygen has got 2 lone pairs, 6 electrons inside the shell. This oxygen, 2 lone pairs, and one of those lone pairs forms a dative bond to another oxygen, and that has its own electrons. So interesting, you want to think about the shape of that. It's got 3 bonding, it's got 3 pairs, doesn't it? We count the double bond laws as just as a single when we're thinking about shape. So it's going to be trigonal planar, but the bond angle is going to be distorted a bit by the lone pair, so it won't be quite 120, it'll be something less than, a little bit less than 120 degrees. Anyway, that's besides the point really, just going off topic there a bit. Okay, now there's another oxygen species which we need to think about here, and that is this one, ClO dot. It's a free radical. Okay, so we draw a dot cross diagram of that. I'll draw my chlorine, do that in green. Oxygen here. All right, we have a single bond there. All right, here's the chlorine, 7 electrons chlorine, yeah, so 6 more, 3 lone pairs. The oxygen, well, that's got 6 of its own electrons. There's 1 there, so we have 1, 2, 3, 4, and 5. So you can see that this is unpaired. So this is a free radical. And we know free radicals are usually very reactive. Yeah. Okay, so now we can talk about how this actually occurs. Well, the compounds which cause ozone depletion, they're usually referred to as, right, the Cfcs, so that's short for chlorofluorocarbons. So these are organic molecules which contain chlorine and fluorine, but strangely, the fluorine doesn't actually cause the ozone depletion problem. It's just the chlorine. So the simplest molecule which could cause this would be chloromethane, which of course isn't a chlorofluorocarbon, it's just a chlorocarbon, isn't it? Yeah, but that could cause ozone depletion. Now, the way in which this happens is that we'll start off with chloromethane there. So if I draw it like this, and if we just think about this bond here, well, we've got 2 electrons in there, 1 from the carbon, 1 from the chlorine. Okay, now you've come across free radical initiation reactions before. Well, if you get some UV light here, that provides the energy to break the carbon chlorine bond. So you'll make a methyl free radical in that case, which is not, we're not really interested in that, but you form a chlorine free radical. Sorry. and then this chlorine free radical can go on to cause some damage. So this is the propagation step. Sorry, this is called the initiation step. So if you want to, okay. Now the chlorine free radical, the chlorine free radical then goes on to react with ozone. And it forms a molecule of oxygen, O2, and a free radical. Okay, so that would be classed as a propagation step because it's a free radical reacting with something that's not a free radical. Then the ClO free radical will then react with another ozone. That will give you two oxygens, two molecules, and a chlorine free radical. That is also a propagation step. So you can see here that the overall effect has been for two ozone molecules to turn into 3 O2 molecules. And we start off with a chlorine free radical, but we regenerate a chlorine free radical. And so that effectively acts as a catalyst. So if you wanted to combine those two equations together, we could write, so Cl dot plus O3 plus ClO to do the reactants this side plus O3, all the products on the right hand side, so that's O2 and ClO dot and 2O2 and Cl dot. Right, cross out anything that appears on both sides of the equation, and you can see the overall reaction then is just 2O3 goes to 3O2. So if you just got one chlorine free radical, yeah, that can cause depletion of, potentially millions of molecules of ozone. And that's what has been happening, okay? So CFCs, they were used extensively up to about 1986, I think, or something. It's used extensively as aerosol propellants. And they used them in that because they weren't flammable, and like the present day aerosol propellants are butane and propane, and they are flammable. These are not flammable. And it was also used as refrigeration. It's in fridges, okay? And every time the fridge was then chucked out, the CFCs would escape into the atmosphere and cause all the ozone depletion. So, well, you may think, people think, all right, well, could chlorine, Cl2, we use quite a lot of chlorine for bleaching and so on. Does that cause ozone depletion? I don't think it does, because that's very reactive. Okay, so it doesn't get up into the upper atmosphere, and it will react before it does. So you won't get no of those free radicals made, chlorine free radicals. Of course, chlorine, we know if you shine UV light on Cl2, yeah, that will make chlorine free radicals, but it doesn't get up in the atmosphere. It reacts with other stuff first before that happens. If we just have a think about, as I say, strangely, it's always, they're called CFCs, these molecules, because they typically did contain fluorine as well as chlorine, but the fluorine is actually not a problem, okay? And that's the carbon fluorine bond. This is stronger than the carbon chlorine bond, and so it doesn't tend to break so easily, so you don't generate fluorine free radicals. As I say, it's the chlorine which is causing the problem. Okay, so that's all you need to know about ozone depletion.